Hi, today I want to talk about line integral. So let's say we have a question here of we are trying to calculate the integral of f of x and y. So it's a two variable function here over a curve, which is a circle in the first quadrant. And then so for a f of x and y, which is three-dimensional. So you can think of it on the xy plane. We have a function, we have a coordinate of x and y, and then this function describe a height for a coordinate for this coordinate. And then by calculating the line integral, we are just basically summing up all the heights along this curve that is described by f of x. So for each coordinates, while we're moving along on this curve, and then there's a height, and then the line integral is basically the sum of the height. So you can think of it as the area for a line that we draw along this curve here. So it's something like the surface area of a curtain. If if it is moving along this curve, the curve. So first of all, let's rewrite the function here, the curve, into individual variables. So for this curve here, we can also write in this format. So x is equal to 2 cosine t and y is equal to 2 of sine t. So basically, and then we are going to calculate ds over dt. So ds dt is just basically we can think of it as the arc length of this of the curve while we're moving around. So let's say if we have a very small value of x and small value of y, and then the arc length of this curve is basically just delta x squared plus delta y squared, take the square root, and this will give us the arc length here. And since we have this format for the variable f, x and y, so that the dx is just 2 times negative sine t, and then dy is just 2 times cosine t. Taking the square and then take the square root, and then this will give us the value for ds dt. So that is just as what's the rate of change of x with respect to t. So here, since we are writing the variables x and y in the verb in terms of t, so t is just the degree of the lines that as we moving along the curve. So basically, if we are talking about the first quadrant, so basically the degree we are talking about is just from 0 all the way to pi over 2. So basically it's just moving 90 degrees for the circle. So we have ds over dt. And now the line integral here is just taking the integral of f of x and y over ds, and let's plug in everything we have uh, um, as we calculate above. So f of x and y it just since x and y is also a function of t, so we can calculate we can plug it in. So basically f of xy is x plus y squared, and plugging in these two variables here is just 2 cosine t plus 4 sine squared t, and we also have ds over dt here. So ds over dt is actually just 2, so we put down the 2 and then dt here. So from start from here, it's just basically basic integral technique. So we calculate over. So in here we have we have f of x and y over the with respect to the curve, and then we expand the integral here, which is f of x with x of t, and then f of y of t, and then with respect to the value of t here. So and then we can input the value for the change in t, which is 0 to 90 degree, and then we have the line integral equal to 2 multiplied by 2 plus pi. So this is the technique or a method to calculate the line integral for this example. And we also have a line integral of the vector field. So basically you will see some question like to evaluate the integral along the curve for this equation here. Given that the curve is a parabola from origin to 1 1. So first of all, let's notice that so we need to check whether this is a gradient field or not. So m is actually the part that is in front of d of x, and n here is just the terms the terms that is before d of dy. So we take the m with respect to d so dm dy, it just we get 21 y squared, and then n with respect to x, it's just 2x. So we find out that dm dy is not equal to dn dx. So this is not a gradient field. So this is a way that we need to check when we are asked to evaluate a function integral like this. So now we find out that this is not the gradient field. We will need to calculate this in the regular in an ordinary way. However, if this two terms is equal, which is also a test for this criteria, which if they're equal, which means there's a gradient field, then we will have another way to calculate the line integral of a vector of a gradient field. So which will be easier to evaluate this integral. However, this is not a gradient field since the test is not satisfied, so that we will need to calculate in the ordinary way. So again, let's rewrite the function. So the parabola is just y equal to x squared. So now we need to separate both variables here. So if x is equal to t, then y is equal to t squared. Then dx is equal to dt, dy is equal to 2t times dt. So let's rewrite the question here. So let's plug t into x and then t squared into y. So we have actually this should be so this should be t cubed t to the power of 6 actually. So we need to plug in x and y in terms of t and t squared into this original function, and then evaluate the integral, and then the range, the limits, the boundary for this integral is no longer x and y. It should be it should be t. So since we are moving from 0 0 to 1 1, so t is actually moving from 0 to 1. So we have our upper lower boundary as t equal to 0 and t equal to 1. And then the integral of this original function in terms of t, and then we get the solution of 1 here. So the integral of our original question is equal to 1. So let's say we so this is the curve. So we are integral this over the curve that is from of a parabola over from 0 0 to 1 1. Let's say we have another path here, which is basically a straight line here. So this is so in our first examples, we are calculating the integral, the line integral that is over this curve here. So now in our second examples, we are calculate the same integral over a different path. So it's from this point to this point here. Even if we are calculating, even we end up the same starting point and ending points, but we have a different curve here. So again using the technique here, and then we actually get the integral. Actually it's still the same from 0 to 1, but the solution of the integral is different. So we have 19 over 12. So even if we have the same starting point, same ending point, and then the same equation to evaluate, but since we have a different path, so we will get a different solution for the of this question here. The reason we are getting different numbers here is because this is not a gradient field. However, if this is a gradient field, and then if we were asked to calculate the integral of this integral over a different path, but if we have the same starting point and ending points, these two numbers will be the same no matter what kind of path we choose, if it is a gradient field. However, in this question, for this function, we recognize that this is not a gradient field by using the criteria here. So so that choosing the different path, we will get a different solution of this integral if we are moving different over different curves. So that's one of the reasons we need to test if it is a gradient field or not. So here we have another question. We have another examples here. So let's say we are going to we are asked to evaluate the integral over this function here. Also from 20 to 02. And first of all, let's check. So m is equal to y squared, n is equal to 2xy minus 1. So and then we take the partial derivative, and then we find out that they are equal. So the criteria is satisfied, and then that means this is a gradient field. So let's say we have three paths here from 20 to 02. So we can either move from from this line here. So y is equal to 2 minus x. And we also have the curve here, which is the partial of the circle. And we also have moving in the x-axis and then moving to the y-axis. So we have three paths we can choose from moving from this point to this point. As I have written down here. So we have three paths here, and then the t, the value of t is also different. For the circle, we have t moving from 90 degrees, and for the straight line, we have t from 0. So since we have we set y equal to t, so t is equal from 0 to 2. And then if we are moving along the axis, then we have two portions. So first, for x, we have two of decrease from 2 to 0. And for value of y, we have value increase from 0 to 2. And so even we have three different paths here, but since this is a gradient field, we evaluate the integral of this function here. No matter which path we choose, we will always get the -2 here. So you can pause the video and also try it yourself to check if these three paths will give you the same solution for this integral, no matter which path you choose. So that is different from our first examples here. So if we have a gradient field, if it is not a gradient field, then choosing different path will give you different solution. However, if you have a gradient field, choosing different path, if you have a same starting point and ending point, choosing different path, it will give you the same solution for this integral here. So so you need to check the gradient field given the integrals here. So that's the first criteria you need to check, and then you might have a easier way to calculate the integral. And also there's another kind of a property you can remember is that if you have a gradient field and your starting point, and then you are moving along the curve, but your starting point is equal to your ending point, then the integral of this function moving along the curve will just equal to 0 if your starting point is equal to your ending point, and it is gradient field you are calculating the integral for. So this is 3 examples actually. So you have to calculate the line integral for integral that is not in the gradient field. You will get different solution choosing different path. If you have a gradient field, you will get the same solution no matter what kind of path you're choosing. Or if you have a close boundary here for in the gradient field, then the integral will always equal to 0. So this is the solution or the technique to calculate line integral in a vector field. So thank you very much for watching.